Welcome to this pre-class video for 331.17. In this class, we're going to talk about three very important types of organic molecules: alkenes, alkynes, and aromatic compounds. When you see the term alkene, then you know that you have at least one carbon-carbon double bond. And be on the lookout for the fragment ENE in the name. If you have an alkyne, then you have a carbon-carbon triple bond, and be on the lookout for YNE. If you have an aromatic compound, then there's many different ways to do this, but in our little world, we're going to stick to what we call the benzene ring. And the benzene ring, the way to draw it in two dimensions is just draw a hexagon and put three double bonds in play. Now, you know from previous discussions that each one of these intersections of lines is a carbon atom. And of course, in benzene, each one of these carbons has to have one hydrogen because each carbon ultimately has 4 bonds. Now, to make different types of aromatic compounds or molecules, you can substitute one or more of these hydrogens and add on other atoms. So when you see a benzene ring, you can say, well, this is an aromatic compound. What I want us to do next is to practice naming alkenes and alkynes. So let's just, for example, let's just take this molecule. Let me draw it out for you. And hopefully this is a legitimate organic molecule. That is, all carbons have 4 bonds and all hydrogens just have 1 bond. And that looks pretty good. I think that'll work. Again, I'm using a condensed formula now. You should be able to work with all different types of formulas, the condensed and a skeletal especially. So the rules for naming alkenes are, you're going to have to harken back to the rules for naming alkanes. Remember, alkanes are all carbon-carbon single bonds. In this case, you want to find the longest continuous chain of carbons that contains the carbon-carbon double bond. And you want to start numbering the chain such that the carbons of the carbon-carbon double bond are the lowest number possible. So it looks like to me we have a couple of choices on where to start. The best place to start is here, because now we've just made this carbon of the carbon-carbon double bond 2. If you start on this side, you will not be able to do that. Of course, you could also make this carbon number 1 instead of this one, because they are really the same. They're in equivalent positions. So let's number. We want to get the longest continuous chain. Clearly, we don't want to go 1, 2, 3 down this way, because we would be done, and we wouldn't include the carbon-carbon double bond, which is against the rules. We want to include the carbon-carbon double bond. So it has to be 3, 4, 5. Now, as you know from previous rules, anything not in the longest continuous chain, we will call it a substituent. And we know this substituent because I've given you on the playbook which ones you need to know. One carbon substituent is methyl. Well, let's put this all together. It looks like our substituent is on carbon number 2, and then we also have to give a location for the carbon-carbon double bond. Well, it starts at carbon 2. So this molecule is named 2-methyl 2. We have 5 carbons in the longest continuous chain. It's an alkene, so 2-pentene. Okay, that's how we name alkenes, and we'll do some more of these in class, but this is to get you kind of ready to tackle these types of problems. Well, what about this molecule? Let me just draw this, and so let's see here. First of all, anytime you see a molecule, you need to think or ask yourself, is this a legitimate molecule? Let me give us some a divider here. Okay, so when you look at this molecule, you should say, oh, I see a carbon-carbon triple bond, therefore I know this is an alkyne. Naming alkynes is very similar to naming alkenes. You want to find the longest continuous chain that contains the carbon-carbon triple bond, and you want to number that chain such that the carbons of the carbon-carbon triple bond are the lowest number possible. So I'm going to start numbering from here. 1, 2, 3, 4, 5, 6. Now back up top here, you may notice, well, it didn't matter up top. Let's just stick to this down here. You've got a choice to make. Before I numbered, I could have made the substituent the lowest number possible, or the carbon-carbon triple bond. I chose to make the carbon-carbon triple bond higher priority in numbering because that's the rules. Okay? Alright, so what do we got? Oh, we have our old friend fluoro. That's a substituent based on fluorine. When fluorine is a substituent, it is termed fluoro. F-L-U-O-R-O. Always spell it correctly, please. And so we have everything accounted for either in the longest continuous chain or in a substituent. So we want to start naming this. This looks like it's going to be 4-fluoro. We always start out with the substituents, and every substituent has a number. 4-fluoro 2. The 2 tells us where the triple bond is located. And we have 6 carbons, so it's hex. And we have an alkyne, so it's hex of I. So I've just given you a couple of examples of naming one alkene and naming one alkyne. Of course, as I've mentioned before, sometimes these naming gets a little more complicated. Sometimes when you have carbon-carbon double bonds, then you have to use an extra special prefix to denote some special geometry of the molecule. Let's say we have a carbon-carbon double bond, and let's call this carbon A, and let's call this carbon B, just to locate them. Okay, I'm going to draw 2 more bonds to each carbon because each carbon has 4 bonds. If carbon A and carbon B have a common atom or substituent off of them, then we have a special type of nomenclature. Let's say we have a hydrogen here, and we have a hydrogen here. Hey, it doesn't matter what else is here at the moment. Hey, carbon A has a hydrogen, carbon B has a hydrogen, and the way I've drawn them, they are locked on opposite sides of the double bond. Now, why are they locked? Because we know you cannot rotate around a carbon-carbon double bond. Therefore, these 2 hydrogens are locked on opposite sides of the double bond. If that's the case, this is going to be called trans because they are on opposite sides. Now, if you have a molecule, another carbon-carbon double bond, let's just label this one A and this one B. Again, this is our way to locate the carbons of the carbon-carbon double bond. If the hydrogens are in this geometry, that is, they are on the same side of the double bond. And ladies and gentlemen, they are locked on the same side because you cannot rotate around a carbon-carbon double bond. So these 2 hydrogens are on the same side. This is called cis. And these are 2 what we're going to call geometrical isomers. They're going to have the same formula, but the arrangements of atoms in space are going to be different. Therefore, the molecules are different, and the molecules can have different properties. Well, how is this going to come up when it comes to naming things? Well, looks like I got ahead of myself here. Let's go ahead and let me delete that because I don't need that anymore. Let's draw. Let me give you an example. So let me draw a carbon-carbon, let me draw an alkene where cis-trans isomers are possible. Okay, so here we go. Again, I'm kind of using the condensed formula. Again, is this a legitimate structure? I say yes. All carbons have 4 bonds, and the bromine has 1 bond. We know it's an alkene, so we know we've got to use the rules of naming alkenes here in a minute. But since, again, I think it's to your advantage, I'm just giving you some friendly advice. Locate the carbon-carbon double bond. Label one carbon A and one carbon B. Is there something the same on carbon A and carbon B? Well, the answer clearly is yes. Each has a hydrogen. The way I've drawn it, are they in a particular geometry? Well, yes, they are on opposite sides. So we know that this is going to be the trans isomer. Now, we just need to number this and name it just like we would any other alkene. I'm going to start here. 2, 3, 4, 5. This is our old friend bromo, the substituent bromo. So when we start writing the name, cis or trans always goes in front. So we have trans. Now let's just name this as always 4-bromo. And we've got, where's the double bond? 2. How many carbons in the longest continuous chain? 5. So pen. This is a double bond. Pen team. And this trans is, let's just call it super important that you include in the name. We only get cis and trans isomers as we've seen for cyclic alkanes and alkenes, not for alkynes. Well, let's just do one more. Okay, looks like again I'm getting, I got ahead of myself a little bit. So let me just delete this and move this one up in place. You may say, oh my gosh, what in the heck is that thing? Well, it's a skeletal structure. You know how to handle these. By looking at it, it is an alkene. It has a carbon-carbon double bond. Then you need to ask yourself, well, where's carbon A? And where is carbon B? Well, here is, I don't want to draw up top for a reason that will be obvious in a minute, carbon A, and this is carbon B. Now I've got to add a hydrogen to A to make that carbon have 4 bonds, and I have to add a hydrogen to carbon B to make it have 4 bonds. But where do I add the hydrogen? Well, you know that carbon A and carbon B each have, or both have, trigonal planar geometry. So the only, ladies and gentlemen, the only legitimate place to draw the hydrogen is up like this and then up like this. That's the only way that you can draw those hydrogens, because we know carbon A and carbon B are trigonal planar. Now, once we do that, something becomes very clear, and what becomes very clear is that this is the cis isomer, because those two hydrogens on the carbon-carbon double bond are on the same side of the double bond, and they are locked on the same side of the double bond. Well, we got that taken care of. Let's just proceed. Again, let's just number the chain. It looks like a double bond is always at carbon 2. That's not the case. It just happens to be in the examples I've done today, but let's just go with it. 1, 2, 3, 4, 5, 6, 7, and these are our old friends chloro, and there's 2 of them, and each substituent always has a number. So if somebody gets me started here, they should say 4,4-dichloro. There's 2 of them. You just can't say 4-dichloro. You just can't say 4,4-chloro. You have to say 4,4-dichloro. Di meaning there's 2 of them. Each substituent has its own number. Okay? Then we keep going. Where's the double bond? It looks like it's at 2. And then it looks like we have 7 carbons. Hep. And this is a carbon-carbon double bond. Heptene. 4,4-dichloro. 2-heptene. Again, all the examples I've done today, the double bond started at carbon 2. That will not always be the case. It just happened to be that case today. Also in class, we will talk about how to name aromatic compounds, but I will leave that for class. I hope this was a useful video to get you started for class today. Thank you so much.